So, today we're going to talk about the invisible force that, well, shapes just about everything. It's what keeps your coffee in its cup in the morning and what orchestrates the silent dance of planets and stars. We're talking about the universe's ultimate connector, gravitation.
All right, let's just jump right in with a puzzle. A puzzle that actually sparked one of the greatest scientific ideas in history. Think about it. A falling apple and the orbiting moon. On the surface, they seem like they have nothing to do with each other, right? One's just a thing that happens in an orchard, and the other is this huge celestial ballet. But are they really that different? Well, it was exactly that question that led Isaac Newton to a totally revolutionary idea, that the very same force is responsible for both of them. I mean, with one single stroke of genius, Newton basically erased the line between what happens here on Earth and what happens up in the heavens. He said there's one universal rule for everything. What Newton realized, and this was the brilliant part, is that the moon is, in a way, always falling. See, just like the apple falls down towards the Earth, the moon is constantly falling around the Earth. This continuous fall is what we call an orbit. It's the only thing preventing the moon from just shooting off in a straight line deep into space. This might look a little simple, but honestly, it's the perfect way to picture how an orbit works. Just imagine whirling a stone on a string, right? You can feel that constant pull. That tension in the string is what forces the stone to move in a circle. The second you let go, poof, it's gone, flying off in a straight line. Well, for the moon, gravity is that string. So this center-seeking force, it's actually got a name. It's called centripetal force. In our little stone experiment, the force is the tension you feel in the thread. But when we look at our solar system, the centripetal force that keeps the moon circling the Earth and the Earth circling the sun is gravity. Okay, so this is where it gets even cooler. You know Newton's third law of motion. For every action, there's an equal and opposite reaction. Well, according to that, the apple absolutely does pull on the Earth. So why don't we feel the whole planet lurching up every time an apple falls from a tree? It all boils down to a really simple relationship from Newton's second law. Force equals mass times acceleration. Now, even though the force between the apple and the Earth is identical, the Earth's mass is just so unbelievably enormous that its acceleration is, well, it's so tiny that it's completely impossible to even detect. All right, so let's get into the actual rules here. Because Newton didn't just stop with the idea. He laid it all out with some beautiful, precise math. This is how we get to a law that governs the entire universe. First up, the force of attraction is directly proportional to the product of the masses of the two objects. Put simply, the more stuff something is made of, the more massive it is, the stronger its gravitational pull. A planet's going to pull way harder than an apple. Makes sense, right? And number two, which is just as intuitive, is that the farther apart two things are, the weaker their gravitational attraction gets. A satellite way out in a high orbit feels a lot less of Earth's pull than one that's closer in. And we're not just talking about a gradual drop-off. Gravity's strength absolutely plummets with distance. This is what we call the inverse square law. If you double the distance between two objects, the force doesn't just get cut in half. It drops all the way down to 1/4 of what it was. This rapid weakening is actually the secret to how our solar system stays so stable. So when you put all of that together, you get this, the universal law of gravitation. It says that every single object in the universe attracts every other object with a force that's based on their masses and, like we just saw, inversely related to the square of the distance between them. This one single, elegant little equation governs everything from apples to planets to entire galaxies. Okay, so this universal law is super useful because it helps us finally clear up something people get mixed up about all the time, the difference between your mass and your weight. And trust me, they are not the same thing at all. So think of it this way. Your mass is the amount of stuff you're actually made of. That number is constant. It's the same whether you're here on Earth, on the moon, or just floating around in deep space. Your weight, on the other hand, is just the measurement of the gravitational force that's pulling on all that mass. And since that force can change depending on where you are, your weight can change too. And that's exactly why you'd weigh only about 1/6 of your Earth weight if you were standing on the moon. The moon just has less mass, so its gravitational pull is a lot weaker. Your mass, the actual you, wouldn't change one bit, but man, you'd feel incredibly light. All right, let's move on to another totally fascinating consequence of gravity, this idea of free fall, and a question that really puzzled people for centuries. Here on Earth, the acceleration from gravity has a very specific value. We call it g, and it's about 9.8 meters per second squared.
Now, what that means is that for every single second an object is falling, its speed increases by almost 10 meters per second. That is a serious pickup in speed. Okay, but here is where it gets completely mind-bending. That acceleration, that 9.8 meters per second squared, is the same for all objects. It doesn't matter what their mass is. A heavy object does not fall faster than a light one. Now, I know what you're thinking. Hold on, I've definitely seen a stone fall way faster than a feather. And you're not wrong, you have. But the reason for that isn't gravity, it's air resistance. The air pushes up way more on that wide, light piece of paper than it does on the dense little stone. If you could do that same experiment in a vacuum with no air at all, they would fall perfectly side by side and hit the ground at the exact same time. Okay, so to bring this all home, let's just take a look at how this one simple law explains an incredible range of things that shape our daily lives and, the entire universe. What's so amazing about Newton's law is how it connected all these things that seemed totally unrelated before. From the simple fact that you're being held in your chair right now, to the majestic dance of the planets, all the way to the daily rhythm of the ocean tides being pulled by the moon and the sun, it's all the same principle at work. Gravity is the great connector. And you see its effects everywhere, even in places you might not expect. The whole idea of weight, which is just pure gravity, is the key to understanding pressure, why a sharp knife cuts and a dull one doesn't. And it's also fundamental to buoyancy, why a massive steel ship can float on water, but a tiny steel nail sinks to the bottom. And here is the final, absolutely astonishing twist. For all of its power, for its ability to hold entire galaxies together, gravity is, by a huge margin, the weakest of the four fundamental forces of nature. The forces that hold the nucleus of a single atom together are trillions upon trillions of times stronger. So if gravity is the weak one, well, that really gives you a sense of the truly mind-boggling power that's shaping the rest of our universe. Something to think about.